What is it?
Yeah.
Oh my God, I didn't hear about that. What do you take? There is not. Have you read the work? Okay, that's gonna better be. Actually, that's not gonna be. Read the Lord of the Rings. Those are two very different. Yeah, yeah. Lord of the Rings is a. There are so many dystopia. Okay, the Hobbit. You obviously I read it. Okay, and furthermore. And that's why you understand because he uses like 18th century English. I mean, at the beginning, like remember, bro was like born in 1890 something.
It's fellow, it's not bro. Anyway. Okay, anyway. Okay. All right. Hi everyone. Welcome to what I believe will be the last data structure lecture or like data structures lecture in the semester. So I plan to basically tell you not everything that you need to know in order to know how Python works, but like most things, so that, you know, in principle, you can then sit down and implement, you know, Python and C. So Dijkstra is pronounced, well, like that more than like anything else, Dijkstra. He's Dutch. Okay, that is the quiz. Okay, all right. The code for Dijkstra is on Piazza, along with the announcement that we're starting lab sessions. So we're doing them, I hope, approximately every day if we can rustle up the personnel. So I'm going to do those for the next couple days. And then maybe sometimes it's going to be a TA, sometimes it's going to be me. Samantha is doing sessions Wednesdays and Saturdays. And so I'm going to do one today at 6 in person and on YouTube, and then tomorrow and on Saturday as well. The plan is to first just for me to go through the labs and to then just have people have the opportunity to come in and work on whatever lab questions that they did not finish during the lab period. And that's just because, you know, there is, you know, not plenty of time, but, you know, a decent amount of time until the exam. It's not time to cram yet. It's actually still time to study. So we're going to do that. We will have sessions, you know, coming up immediately before the exam where we will be less principled about it and just tell you, you know, okay, like if you're completely lost, this is what you need to know now. For now, what we're doing is we're just trying to get everyone to do the labs, perhaps with help, because that's the way to study. There is no, did they tell like the Royal Roads parable in this class this year yet? I don't think I did. The story goes that Euclid was hired as, you know, the tutor for some, you know, Greek prince, whenever that was. Euclid would be 300 BC or something like that, and started giving the prince problems in geometry, and the prince complained, well, like I'm royalty and you are giving me exercises. What's up with that? Isn't there some kind of shortcut that you can give me? To which Euclid famously apocryphally replied, your highness, there are no royal roads to geometry. So similarly, no royal roads to hello. No royal roads to ESC 190 either. So okay. All right, okay, so I want to talk just briefly about the Dijkstra code and to add one line to it, which will recover the path as well. So this is the code from last time. There was one bug there, which is the set here was initialized with having visited the start node already. Obviously, if you've already visited it, then what happens is you pop it from the queue and you continue and nothing works. So here we put the start node in to be considered. We don't visit it yet. In this particular case, what we do is we terminate when the end node is reached. So that means that once we've added the distance from the start to the end node, we terminate. We don't keep trying to determine the distance to every other node because we're just looking for the shortest path to end. You could also just keep going until to be considered is empty, which means that you've run out of nodes to determine the distance to. So, okay. So the way it would work with this code, so I'll first do the input, is so again, to remind you, so what we have is we have nodes and we have connections, right? So a node has a list of weighted connections associated with it. So the list of weighted connections is just tuples that are the node that we're connecting to and the weight that's associated with that connection. Okay. And the way we work with this is, so we make some nodes. So for example, YYZ, LAX, YUL. And then here we make a connection from YYZ to LAX, and we say that that costs 1,000. And then we add a connection, for example, from YYZ to YUL, and that costs 300 or something like that. Make sense? Are you with me? Okay. So, all right. So that's how that works. And again, so this is the Python. What's the key here? The key here is we maintain a queue of nodes to be considered with the associated cost of going via with the associated costs, right? So when we say, okay, let me visit one from the queue, the thing that I'm visiting is, okay, this is too entertaining. So the thing that I'm visiting is the node with the cheapest possible path. Okay. Does that make sense? So what do I mean by the cheapest possible path is, out of all the nodes that are to be considered, I'm looking at the one that has the lowest of those guys added previously. So we add all the to be considered nodes. When we visit a node, we look at all its neighbors, so its connections, and say, this connection is going to cost me this much. Make sense? If I go through the current node. So let's say that I want to be able to actually recover the cheapest path once I determine what the cost of the cheapest path is. So what that means is when I pop current over here, I will need to know how much it costs, but I am about to visit it, and I need to know where am I visiting it from. Currently, I don't know. Does that make sense? Because currently, I know how much it would cost, but I don't know how to get there. So in order to know how to get there, what I need to do is, in addition to saying that I want to consider this guy, I want to also say that I would get there through the node that I just visited here, so that I would get here through current. Does that make sense? So that means that I just need to write that down. So one way to write that down is to say, well, so I'm pushing this guy, and then I'm saying, okay, so the node is going to be con node. And then I also need to say, not this. So I also need to say what the previous one is. And the previous is current. Let me close this, and close this, and close this. All right. So rather than saying, okay, so into the to be considered queue, I'm saying consider node with this cost. I'm going to say with this cost, and this is the node, and then the previous one is going to be current. So then when I pop it off the queue, this would be like current dictionary. And I'll say that current is current dictionary node. And previous is current dictionary previous. And I'm visiting it, right? So what I need to do is I need to just record that I'm visiting it. The easiest way to do it is to just say, okay, so I have my current node. And I've already visited it. So current.prev is just going to be prev. Because when I visited the node, I already know the distance from start to that node. And I know that it's going to be through prev, because when I pushed it, I specifically said this cost, you only get it if you go through prev. Yeah. Where did I define? So I define so here I'm pushing this guy, right? So previously I was just pushing con node into the queue. And now what I'm doing is I'm pushing this guy. And then when I'm getting it back, I'm getting current distance, current dictionary. So current dictionary is whatever I pushed over here. So I'm naming it over here. Yeah.
No.
Current is a no.
We define the value current.rev in our class.
No, so I'm doing it now. Okay, so in Python, you're allowed to just say, I'm going to have another attribute for the object, right? If you remember. So like in Python, like that's not a problem. So like for anything, right? So for anything, I can say like A is like a dictionary. A dictionary, maybe not. And then I say like AB is yeah, so the dictionary is not going to allow it, but like a function. Right? So that's a function. And then like I can say like FB is 1, 2, 3, and now there's also FB. And F is still a function, but it also has a dot B if I want to access it. Okay. So, all right. So, do people understand this transformation here? So what they did before, so what I'm doing here is into the queue of to be considered, I'm adding, this is how much it's going to cost if I go through current, and then I record the fact that this cost is actually associated with going through current and not with anything else. Does that make sense? All right. So once I have that, so here, let's say, let's say first that I want to go from YYZ to YUL. What is it not happy with? No such file or directory. Oh, because I need to quit this. Node is not subscriptable. The current dict. Hold on. Yeah, I think I had like an extra. Okay. Not sure what it's thinking. So current dict. Oh, because yeah. So here we're going through start and we need to say, so this should also be a dictionary. Okay, sorry, I got to restart, I think. Okay. All right, so previous none, I need to close this parentheses, like so. And now we're good. Sorry, so the change was I forgot to also now push a dictionary with both the node and the previous into to be considered over here. So now it's consistent, and now here, so this is like a simple one. So I want the cheapest cost from YYZ to YUL, which is obviously 300. So that's good. And then in order to get the path, well, the path is not really difficult because the previous to YUL is YYZ. So if I just say previous, so here, the way it's defined is the node has a value, which is like the name. So I'll print the name. And here, now the previous to YUL is recorded as YYZ. If it were a longer path, you could get the path. Let's do a longer path, right? So I'll do like one more. So whatever, YYY is YYY, and then I'll connect that to YUL. And now I want to get from YYZ to YYY. And now I want to go down to YYZ from YYY, right? So the way I would do it is I would say current is YYY. And I'll keep going back. So I'll print the current airport, so YYY, and then I'll set current to current previous in order to go back to the previous one. That's the shortest path. Cool. Does that make sense to everyone? No? So basically what I do is every time I visit, I also take note of where am I visiting from. The reason I can know that is that that's the algorithm, right? So I have a priority queue of which is the thing to visit and what am I visiting it through. Yeah. Say again? Say again? I am, yeah. So I am printing it, and that's the only way, right? So I can know what the previous is. I could in principle say, so I could in principle, if I only care about getting to the end, even then I couldn't really record it forward, because if I say like current next, it's unclear. It's like current next going where, right? Because current next, depending on where you're going, it's going to be different. So I have to record the previous. Okay, does this make sense? Okay, cool. Okay, all right. So that is Dijkstra. How many people feel like recognizing that maybe this is like there is a selection bias? How many people feel like they understand how Dijkstra works? Okay. All right. I'll give it one more go. So what are we doing? Our goal again. So let's, like, that is like conceptually, I think, the most difficult one. So it doesn't like surprise me. So again, like, what are we trying to do? We are trying to find the shortest path from the source to basically everything, except we want to be able to just stop if we want to when we've determined the shortest path to whatever end node we're thinking about, right? So the way we approach it is we say we have a set of nodes that are visited. Those are the nodes for which we already recorded the cheapest path. And now the key insight in Dijkstra is if you already have nodes that are visited in a particular order, according to Dijkstra's algorithm, you can figure out which node to add next, for which you will definitely know what the cheapest path is from the source. Right? So that's the theorem that's kind of hard to prove. We did a sketch of the proof before, which I'm not testing you on. But that's like the key insight, which you should just box in and not worry about. Okay. So absent that, what is the algorithm? The algorithm is to say, I have my visited set. So that's like the gray area here. and I'm looking to add another node to the visited set. And the rule is this node is supposed to be such that in order to get from S somewhere inside the visited set plus the edge to outside the set is as cheap as possible. That's the rule in Dijkstra. Okay. So if I'm adding V, it's because S to some U plus the edge UV is as cheap as possible. U is inside the visited sets, and then V is outside the visited sets. Okay, so that's the rule. Yes.
Of course, we can get to that from like the path to get to that node is the same as
Not necessarily. So what we're saying though is that the node which is cheapest to get to from S to outside the visited set is the one for which we know the cheapest path. That's the theorem. Right? So it's not that for any, it's true for any node, it's not. It's true specifically for the node for which S to U for some U plus UV is as small as possible. Okay, so that's the rule according to which we're adding the nodes. And if we're adding the nodes in this particular order and recording the distance in this particular way, then by theorem, that actually gives you the shortest path. Does that make sense? Yeah. Yeah.
So what if you go from U to V, and then that is the cheapest path at that moment, but then after V, there's something more expensive, how do you account for that?
Well, if it's more expensive, that doesn't matter. You're asking what if there is something cheaper? And the theorem is there isn't anything that's cheaper. And that's a theorem, right? And if you remember, like we went through the reasoning for why. We said, okay, so like, why is it that if S to U plus UV is as small as possible currently, there isn't going to be a cheapest path from S to V any other way? And the short of it, again, I'm not going to do like the formal thing, but the short of it is, well, what else is it going to be? If it were like S to X plus XV, then by definition, that's not as cheap because S to U plus UV is as cheap as possible. And if it's that you just haven't visited the right node yet, so it has to be like S to X plus XY plus Y to V, well, that's already more expensive because S to X plus XY is already more expensive than S to U plus UV.
What I'm wondering is like, let's say going from S to U to V is the cheapest right now,
Yeah.
but then S to U to V results in a path afterwards that you have to go on, but it's more expensive than say going from S to X.
I mean, if it's more expensive, we don't care. Like we care about finding the cheapest one, right? So like we care about if we visit V, then we record the cost from S to V, and that's supposed to be the smallest one. There's definitely going to be something more expensive, but that's fine. We already recorded the cost from S to V. Yeah. So the claim is that if you record the distances in such a way, so according to Dijkstra's algorithm, so if you record them like this, where U is such that U is in the visited set and DU plus the edge UV is as small as possible, then this is correct. Then the distance to V from S really is the distance to U plus the edge UV. Okay. So, say again? The last part meaning the proof or the claim? Okay, so the claim is that if you add visited nodes in this order, right? So if you say that the way you select V is to find S to U in the visited set plus the edge UV outside the visited set, such that S to U plus the edge UV is as small as possible, then it is true that the cheapest path to V from S is this much.
To say if you choose the visited path, the cheapest path, then that cheapest path is the cheapest path.
No, it's not obvious because it's not obvious because you might imagine like so like there is like like the famous like Richard Feynman joke about like any theorem being either false or obvious. And I guess this one is true. So I guess that's obvious. But it's not obvious because you might imagine, well, like you just have the visited set. Like maybe you can go through something that's in the non-visited set, and that would be cheaper.
S is in the visited set.
S is in the visited set, but it needs to be through the U, which is also in the visited set. So the counter argument would be, what if you go through some node to V that's not in the visited set yet?
But by definition, if you was in the visited set, then that means that's the cheapest path from S to U, then that's the only one.
Yeah, but what if you go not through U, but through something else?
Well, by definition, what would be the cheapest path?
I mean, I can't argue with you because the theorem is true. So the question is whether it's obvious or not, right? But the reason it's not that obvious is you have so here we're selecting the V specifically so that you go through something that's in the visited set, right? So the thing that could happen is like maybe you need to go from S like to here and then from here to V, and that would be cheaper. It wouldn't be, but that's the thing that you need to argue against.
So you the cheapest.
No, not necessarily. So it's just that it turns out that that's the case. DU, DU, no. So DU is the cheapest path from S to U.
Whatever distance that's going to be the cheapest distance.
So only if it's the case that S to U plus UV is the smallest possibility. So it wouldn't be the case if, for example, necessarily it wouldn't be the case. Like imagine that S to X plus XY is really cheap, and then Y to V is really cheap. Then it could be that the cheapest way to get from S to V is S to X to Y to V. Could be, right? It's just that the way we selected V is S to U plus UV is as small as possible, smaller than S to X plus XY, which means that S to X plus XY plus Y to V is definitely larger, but you need to argue that.
If you pick the cheapest path, if we pick the cheapest path, then the cheapest path is the cheapest path.
No, because this is picking the cheapest path available right now. It might be that, so I mean, yes, it is the cheapest path. So in that sense, yes, but you need to argue that the cheapest path that's available right now is the cheapest path that's ever going to be available. Okay, because it's restricted to. So the paths that we are considering are restricted to S to what's already visited plus an edge from visited to non-visited. So it's not all the possible ones. It's just S to visited plus from visited to unvisited. Okay. Make sense? Okay. Is that better conceptually? Any objections? Okay. So now the modification with the priority queue was that what we do is anytime we visit something, so when we visit U, we immediately put V in the priority queue and say, well, like if you were to visit V through U, then this is how much it would cost. And then we have this to be considered U, where we can get the smallest, where we can get the cheapest possible available node to visit right now. And the advantage of that is that priority queue can be efficient, so you can retrieve the minimum priority node from the queue in all of log n time. Make sense? Okay, questions? Yes.
just a question about like graph traversal in general.
Okay.
So are depth first, breadth first, and Dijkstra, can they all be used similarly, like in similar scenarios?
So they're different in the sense that graph traversal is just about listing out all the nodes. It's not a graph traversal does not try to find the shortest path in any sense. Dijkstra is for finding the shortest path.
Right, but like you can use each one.
So you can use Dijkstra for graph traversal, I guess is what you're saying, and that is true.
Right.
Yeah.
Like to follow up, like if you're trying to search for something, you can use all three, but Dijkstra will do it in the shortest way possible.
No, Dijkstra would not do it in the shortest way. So Dijkstra will find eventually the shortest path. It's not going to do it in the shortest way possible. Its output is what is the shortest path.
Like I'm not saying that that's the shortest, but the path is.
It will find what the shortest path is. It's not going to take the shortest. It's going to take the shortest path among other paths, right? But it's actually going to try different things. So, and another way of saying it is, while you can use Dijkstra for graph traversal, because eventually it will reach every node in the connected graph, it's not the case that that's the most efficient way to do graph traversal, because Dijkstra actually needs to go to the same node several times potentially. Okay. All right, so are we good with this and with the priority queue now? No? Yeah. Okay, so the priority queue is about, rather than kind of de novo saying, well, like I need the V such that S to U plus UV is as short as possible, what you do is ahead of time, anytime that you add a node U, you say, well, like I'll look at all the neighbors of U and I'll record how much it would cost to get to every neighbor of U through U. And then when I need the cheapest S to U plus UV, I already have my priority queue. So I'll just pop the thing with the cheapest cost from the priority queue. Say again? I just build it, right? So that is what I do here. So I have my queue, I call it to be considered. And then every time I visit a node, so this is visiting current, I'm saying, okay, so for every neighbor, I'll push this neighbor, so connection node, to the queue and with this cost associated with it. It means that I say that this queue is going to have this object associated with this priority. Sure. Okay. All right. So that's like this. So I now want to briefly talk about better graph search. So what we were talking about last time in the last few minutes is looking at graph search by talking specifically about those kinds of graphs where every square is connected to every other adjacent square, except if there is a barrier. So you can draw, if you go to this website, you can like draw the barriers, right? And then we can say, okay, so what if I do breadth first search and I disallow diagonals? So that's what it's going to be. And eventually I'm going to find the red, right? But takes a while. All right. Cool. So I can do it like that. I can also say I'm going to try Dijkstra on this. But disallow diagonals again. So that looks kind of the same way. And the reason is what we do every time is we just explore all the neighbors of the already visited nodes. Okay. So what this is are people clear about how this is a graph? Do we, so let me briefly flash the picture that we had. So like if this is like this, so basically like every square is a node, and then like this node is connected to this square is connected to this square, but it's not connected to this one, right? So this is why like there's like arrows here, but there's no arrow here. And cheapest path here is just the smallest number of jumps. Okay. So Dijkstra eventually is going to find the cheapest path, but it's going to need to explore a lot. So one possibility is, well, like I know that in order to get from green to red, like if you're playing a video game and you're trying to get your character from green to red, you're just going to try to press right, like as much as possible, right? Because you want to get to the red square. So that is basically what best first is. So again, I disallow diagonal. So best first is basically go in the direction of the red as much as possible. And by in the direction, we just mean like make it so that the distance, just Euclidean distance on the plane between where you are and your destination is as small as possible. If you can't do it, just make a turn. Yeah. It would, yes. Yeah, it would. And you're right that in general, maybe you don't know, right? But sometimes you do, or sometimes you have an idea. And that's exactly the formalization, right? So we are on those slides over here. So if I can tell how good the current node is, probably, then I can use something like best first. So imagine that we have what we call a heuristic function, h of node, and it's an estimate of how far the node is from the destination. Sometimes you don't know, but sometimes you do, or sometimes you have some idea. And then if you have that, then one thing you can do is just say, okay, like I'm currently here and I want to go to the node that's not visited, that's a neighbor, for which the heuristic function is as small as possible. So in the case of doing pathfinding, if you know the coordinates, but you don't know what to do about the wall, then just the Euclidean distance between where you currently are and the destination would be a reasonable heuristic. Does that make sense? Yeah. It's a function. Yeah. So it's a function, and it's going to be dependent on the problem. So in the case of this problem, like the answer is, if you know that your problem is you're trying to get to some coordinates and you need to go around the walls, then one possible function is what is the distance between where you currently are and the destination. So the distance just in the sense of like as the crow flies. Does that make sense? So that's all it is. That's best first. Right? So just try to go to whatever seems the most promising right now, according to some definition of most promising. In the case of trying to find a path, most promising means the closest. Obviously, you can go wrong this way, right? Something that looks promising might be a really bad idea, right? So it might be that, let me reload. So it might be that like it seems like it's really promising to go to the right, but then like here is blocked and here is not blocked. And here is blocked. So I'm gonna do best first here. not allow diagonal. So here, like eventually, like when you get to here, you know where to go. But up until the point where you get to here, lots of things seem as promising as trying to go down. Right? So it might not be great. Does that make sense? So does best first make sense? So some heuristic function. So it works to the extent that the estimate, the heuristic function, is actually a good estimate of how good the node is, so how far away it is from the destination. So here's how it might work. So if you have, a greedy search where you do best first, then in this kind of situation, what you would do is you would go to the right because the destination is on the right. But actually what you wanted to do is to go down this way. So it's not going to find necessarily the best path. So one idea is, why don't we combine the why don't we combine the idea of best first? So the idea of doing kind of going to where it makes sense with something like Dijkstra. And that's called the A-star algorithm. So the A-star algorithm is basically the same as Dijkstra with one difference. So the difference is that when you are assigning the priority, so this is Dijkstra, except when you're assigning the priority is the distance from the source to the point where you are, plus the estimate, plus the heuristic function, plus the HV. That's the only difference from Dijkstra. Okay, so the idea here is the nodes that you want to explore first are the ones where the sum of the estimate of how close you are to the destination plus the shortest path from the source, or the estimate of that, is as small as possible. Okay? That's it. That's the only difference from Dijkstra, is rather than the priority being just the what's the shortest path, the priority in terms of what you visit, the priority is shortest path plus an estimate of how good this node is to explore in terms of how promising it is in terms of getting to the destination. And this is not, so under some circumstances, it might get you the best answer, under some circumstances not. This is what's called heuristic search. It just works better usually. And that's what people use in usually in video kind of non-player characters and video games and stuff. If they want to go somewhere, that is what they use. And that is what that's going to look like.
So is H a function that you implement like a help function?
Yes. So H, and there's different kind of situations. So far I just gave you one example of H. If you are trying to find the path around walls, one H that makes sense is just the distance as the crow flies to the destination. Right? It might be not necessarily a good estimate of how good the node is, because it might be that you're walking into a trap where everything is walled off, but it's something. Right? So A-star is basically combining those. It kind of works. So, okay, we are at 12 o'clock. People are leaving. Okay, I will see you. I promise to start AI on Monday. I will, but there's gonna be 20 more minutes of algorithms, I guess. Okay, I'll see you. Bye.